what does x of minus z do? And to answer this question, we put z equal to e raised to the power j omega, as we always do, to interpret things in the frequency domain. Now, when you replace z by minus z, you are replacing e raised to the power j omega by, well, minus z is e raised to the power plus minus j pi times e raised to the power j omega for z equal to e raised to the power j omega. Recall that e raised to the power plus minus j pi is minus 1. So, now we have an interpretation for multiplication by minus 1 in the z domain. Essentially, we are replacing e raised to the power j omega by e raised to the power j omega plus minus pi. In other words, we are shifting on the omega axis by either pi or minus pi. Now, it should be noted that shifting by pi and shifting by minus pi are the same thing. That is because there is periodicity on the small omega or the normalized angular frequency axis, a periodicity with a period of 2 pi. So, there is no problem if we replace plus pi by minus pi there. Shifting by plus pi and shifting by minus pi are the same thing. With that little remark and observation, what we have done in replacing z by minus z as far as the normalized angular frequency is concerned is to shift by pi, whether plus pi or minus pi. And we would best understand what this shift implies if we took an example spectrum. So, let us take an example spectrum to complete this discussion. Let us take this spectrum. Consider an idealized spectrum like this, essentially with lines lying between minus pi by 2 and plus pi by 2 and 0 outside. So, this is the spectrum of some sequence. Let that sequence be x of n. So, this is the normalized angular frequency omega. This is capital X of strictly e raised to the power j omega. But as you know, in discrete time processing, we sometimes abuse notation a little bit and we write just capital X of omega instead of capital X of e raised to the power j omega, which is more correct. But anyway, I must emphasize that as far as we are concerned, from the context, capital X of omega and capital X of e raised to the power j omega essentially mean the same thing. Now, with that remark, what happens when you shift by pi here? So, recall that actually this is what x e raised to the power j omega is. So, we will do a bit of zoom here. All right. Periodically repeat it. With a period of 2 pi. This is what x of e raised to the power j omega actually is. can visualize, if you shift this either forward or backward by pi, it is going to give you the same thing, and what is going to appear after shifting by pi is the following. Would therefore appear like this. Again, we shall do a bit of zooming here. And so on here. And so on there. So, now your triangles are around pi and then 3 pi and so on, and here around minus pi and then minus 3 pi and so on. So, now again if you take the principal interval which is here, this is what we get. Now, we must be a little more explicit in our relationships here. So, in x of e raised to the power j omega, if you look at the principal interval minus pi to plus pi, we notice there are two segments here for the positive side of the omega axis and the negative side of the omega axis. Let us call the segment for the positive side A and the segment for the negative side A bar, and in fact, there is a reason for this. You remember that the discrete time Fourier transform has conjugate symmetry for a real sequence. So, it is with that reminiscence that we are writing A and A bar. I agree that if the sequence is complex, this conjugate symmetry would not be there, but very often we deal with real sequences, and therefore, it is useful to put the symbols A and A bar there just for emphasis. Anyway, now what we will do is, in x of e raised to the power j omega plus minus pi, we shall mark the a's and the a bars carefully. So, here again in the principal interval, this was actually a and this was a bar, is not it? And therefore, this was a and this a bar. And now, what we need to do is to expand the principal interval for our convenience. So, expanding the principal interval, this is what we get. We get an a bar here and we get an a there. Now, just for convenience, I shall show in dotted on the same diagram what we had just for capital X. So, what I am saying is the solid lines here are x omega plus minus pi. And I shall show in dotted x omega, just to be clear. Again, forgive the abuse of notation where we have replaced e raised to the power j omega by just omega for clarity here. All right. So, in x of omega you had a here and a bar there, and now you have a bar here and a there. So, what has happened is in effect these so called negative frequencies between minus pi by 2 and 0 have now appeared between pi by 2 and pi. So, two things have happened. The order of the frequencies has been reversed. So, for example, in principle, a frequency let us say of minus pi by 4 here is more than a frequency of let us say minus, here you would have 0, pi by 8, pi by 4, 3 pi by 8 and so on, and the same on this side. So, if you take a minus pi by 8 frequency here and then a minus pi by 4 frequency there, the minus pi by 4 frequency appears as a smaller frequency here. One can see that, because the order of frequencies from 0 to pi or 0 to minus pi by 2 has been now reordered between pi and pi by 2. So, increasing magnitude of frequency here becomes decreasing magnitude of frequency there. Secondly, the frequencies themselves change. So, actually this is exactly what happens in what is called aliasing. Many of us will recall from the theory of sampling and aliasing. This is something very fundamental. In a course on discrete time signal processing, or in the process of sampling a continuous time signal to get a discrete sequence, these things happen. So, if we do not sample at an adequate rate, we get a problem called aliasing. What is aliasing? Aliasing is a phenomenon where a sine wave assumes a false identity, and there are two things that happen in aliasing. One of them is of course that the frequency of the sine wave appears to change. The other is that when you increase the frequency of the sine wave, the apparent sine wave or the sine wave produced by impersonation, if you would like to call it that, seems to have its frequency reducing. So, an increasing frequency, an increasing actual frequency seems to appear as an apparently reducing frequency. These two things together they together make up the concept of aliasing, and what we are seeing here is just an instance of aliasing. Why are we seeing aliasing? It is not very difficult to understand. What we have done is to downsample. In the process of downsampling, we have in fact introduced the possibility of aliasing, and this x of minus z term is bringing before you the consequences that would be there if aliasing were allowed to remain. Think about it. X of minus z is therefore called the aliasing term, because it tells you the contribution of possible aliasing. In the two band perfect reconstruction filter bank, which we shall soon see, this aliasing should be absent. By perfect reconstruction, I mean if y is to be an exact replica of x, as is the case for example, in the Haar system when you have chosen the filters properly. So, you analyze or you decompose and then you synthesize or reconstruct, and if the reconstruction is perfect, there should be no aliasing. So, this x of minus z term is a troublemaker term in general, troublemaker in this sense. Let us make a note of this. So, the x of minus z term or equivalently the x of minus e raised to the power j omega or x e raised to the power j omega plus minus pi term is the consequence of aliasing.